Okay, hello everyone. Thank you for coming to this RAL seminar. So today we are very happy to have Professor Zhonghua Zheng from University of Manchester, UK, visit us and give this exciting seminar titled Towards More Accessible AI-Enabled Urban Land Service Modeling. So just a bit background for Zhonghua. So Zhonghua is an assistant professor tenured in data science and environmental analytics at the University of Manchester, United Kingdom. He is also the co-lead for environmental data science and AI at Manchester Environmental Research Institute, MERI. His research interests include environmental data science, aerosol and air quality modeling, and urban climate and environment. So he received a Master of Computer Science degree and a PhD in environmental engineering in civil engineering with a concentration in computational science and engineering. Both from the University of Illinois Urbana-Champaign, UIUC in US. So he is an editor for the journal ACP, stands for Atmospheric Chemistry and Physics, associate editor for the journal Atmospheric Environment, and the vice chair of the American Meteorology Society AMS Artificial Intelligence AI Committee. Yeah, so the floor is yours. Sure.
All right. Thanks, Chen-Ling. It's my great honor to be here. Yeah, although I was an ASP postdoc about 4 years ago, it's my first time to be in this campus. Yeah, I was in Mesa Lab. Okay. Okay, so today I'm gonna talk a little bit about our recent progress in urban land surface modeling. And sometimes I will say urban climate modeling, but urban land surface modeling can be a part of either the urban weather modeling or urban climate modeling. So when you hear I say something about urban climate modeling, don't be confused. All right. So most of the work were done by my PhD students. So currently I have a group of 8 or 10 PhD students, and here are just 3 of them. The work are based on their these students' PhD dissertation, and I also have a lot of collaborators, like Professor Lei Zhao, who is my PhD co-advisor, and Dr. Keith Olsen here at CGD, and some colleagues in Europe, and Chen-Ling here. All right, and also this work has been funded by, the works here are funded by UKRI, which stands for UK Research and Innovation, and industry partners such as AWS and NVIDIA. All right, so I would like to get started with like a brief background regarding global climate change. Although I think most of your audience online are familiar with this. Here, I just select some pieces of news. For example, this one, it has been confirmed like we hit the warmest year on the record in 2023. And then in 2024, we broke the record again. And then in 2025, even without setting a new record, we still reached the 2025 was still one of the warmest year on the record. And those aren't just numbers, so they are the warnings to us, right? On the other hand, why do we care about urban areas? So we have like the Earth surface, assuming for sure it's 100%, and then we have 30% for the land and 70% for the ocean, and within the land areas, we have the urban areas, right? Guess how much the percentage the urban areas account for? It's only about 0.5 to 3% of the land area. Those can be classified as urban. However, we have more than 58% of people living in the urban areas. So, so that's based on the World Bank. The information from the World Bank. And in the UK, it's like 84% of the population living in the urban areas. However, in 2050, based on the United Nations projection, we will have more than 68% of people living in the urban area. So you can see the number. Land accounts for 30% and urban accounts for 0.5 to 3% of land area, but it holds more than will be more than 70% of population in the next 30 years. So this highlights the importance of urban areas, and we need to study either the weather and the climate over the urban areas. Here, I don't know, I think most of you might familiar with this term called urban heat island. So this refers to urban areas usually experience this effect, and because they are more significantly warmer than surrounding rural areas. Here is an example. You can see we have the downtown, and in the x-axis we have downtown, we have the urban residential, we have suburban, and then we have rural area. And then you can find the temperature. The y-axis means the temperature. You can find over the downtown area, we have higher temperature, and in the rural area, suburban area, you can find the temperature are lower than the downtown area. So this is called urban heat island. And there are many factors that account for this, like the impervious road, like the urban canyon effect, and etc. I will give more information regarding this. However, I would like to highlight although urban area is very important, we have very limited true urban representation in global weather stations. So here I use a figure to show that the pervious surface fraction for the different weather station, the land type, and then I select several stations. And you can find that those stations are not really in the urban areas. So that means if we use those data to build a model or to do the data simulation or use this data for analysis, there will be bias because those are from the rural area, not the real urban areas. So the temperature might be lower than what it should be. So you can see if we use the temperature from rural area, then we may underestimate the risk compared to the one in the urban areas. So that's a motivation why we want to study the urban areas and why we need to use a better urban land surface model in order to demonstrate and to do the future projections of urban heat. So for today's presentation, I'm gonna illustrate our research progress from 3 areas. The first one is a multi-scale urban land surface modeling, and the second one is enhanced urban land surface modeling. I will give some examples regarding why we call it as enhanced modeling. And then I'm gonna give some examples regarding AI and cloud computing for urban land surface modeling. All right, so let's get started with the first one. I call it multi-scale urban land surface modeling. Here are some examples of the urban areas. You can see we have the buildings, right, and then we have the road, and also we have the rooftop. So to simplify this model, people use something called the urban canyon model to do that. So you can see for the urban canyon model, we have the roof, we have the wall, we have the road, and the people use this simplified representation to study the urban. So it's much more complex, compared to just demonstrate those 3. We call this the column or the urban surfaces. You can see we have the radiation, we have the building energy, we have the turbulent fluxes, and we have hydrological those processes within this building. So you can see, for example, we have sunlight coming, then it might be trapped within the urban canyon. So that's one of the reasons why we have a higher temperature for the urban areas. And on the other hand, we have the Earth system models. Now more and more people talk about the K-scale modeling. So that means we want to use Earth system model to have higher resolution to represent the dynamic system for the globe or for the certain areas. And the Earth system model is one of the to-go choice in order to do that. And because Earth system model, they can simulate the vertical and horizontal interactions and the different components, the interactions among different components. One example is a CESM, right? Developed by NCAR here and by the community. We have the land model, we have the atmospheric model, and it's a state-of-the-art computational simulation and fully coupled. That means we can turn off certain components and to simulate the interactions between these components. And within the land model, then we have the urban model. So urban model is within the land model, and you can see we have the vegetation, crop, and the glacier, those kind of land models with those kind of modules within the land model. And then basically we use an atmospheric model to drive the land model, and then to drive the urban canyon representation to get the temperature, relative humidity, and other variables from the land surface model. And this is more complex process. I won't dive into this, but just let you know, like it's not a trivial work. There are lots of processes going on, and also this model can simulate indoor temperature because it has been incorporated into a simplified building energy model. So one of our studies, like basically to study the interaction between the building and the outdoor environment. This model was developed by Dr. Keith Olsen at CGD, and the first paper was published in 2008. There is an updated version published in 2019. The new capability, basically one of these is the building energy model. Then this model has been widely used in studies regarding the urban climate. For example, this model has been used to study the contribution of local background climate to urban heat island, has been used to study the heat risk in wet climate, and then used to study the impacts of solar panels on global climate, and also the climate-driven biophysical feedback that also the interaction between building and the urban climate. For the global scale, because I mentioned I'm going to talk about the multi-scale. So by default, if we use CSM, we are doing something like global simulations. And for some of the simulations from CSM larger ensemble, or CSM1 larger ensemble, CSM2 larger ensemble, the data is publicly available. Then we can download this from the Geoscience Data Exchange, and also they are available AWS Cloud. So I also developed some tools in order to retrieve those data and also to show the demo regarding how to make use of the data. Then on the other hand, with those data, those big data, we can consider how we can use an AI approach to build a relationship. One of the approach we call is a data-driven emulator. What we call emulator is like we want to make use of the connection, the relationship between the atmospheric model and the land surface model. For example, we consider this as X, the atmospheric model as X, and the land surface model as Y, and then we want to build a relationship between X and Y. The reason is like we can get the atmospheric input or output from many models, not only CSM, but the other Earth system models or even from WRF. Then based on those features, we call this as a feature or predictive variable, then we can get the urban land surface model. Then it's a surrogate model or emulator to speed up the process to simulate urban variables. Here's an example, say, in order to use this model, for example, what we are interested in is Y, right? Y is urban land kind of variables, urban temperature, urban relative humidity, and so on. Then we can use the F. F is what I'm going to show you how can we get F. Use F and X. X is atmospheric variables from atmospheric model. Then we use supervised learning. What we call supervised learning is like you provide pairs of Y and X. Then we use supervised learning. You can consider it's like linear regression is a kind of supervised learning. We try to use the Y and X, and we fit the mapping function. Then in the future, when we have X and F, then we can get Y. That means we don't need to run the urban land surface model again. So here's a process. We have X, we have Y, we derive F, and with this F, then with the X from different Earth system models, such as the GFDL model, the UK model, etc., then we can get Y for all of these models. So this is how we developed the emulator and how we applied emulators for the urban climate. So we developed the emulator for the daily scale and the monthly scale. For the daily scale, we also try to identify to quantify the structural uncertainty for the heat wave projections in the future. And then the monthly emulator, we use this to study the local urban climate and to the projections for the future. So those are the studies for the global scale. Then on the other hand, we have the single point simulation, because when people develop those kind of urban land surface model, we will start from the single point simulation. And the CTSM basically provide the tutorials or instructions regarding how to use the single point simulation. However, when we try to use those simulations, especially for the stakeholders who are not familiar with coding or Linux or something else, it's very difficult for them to implement that. So that's one of my part of my title, that how to have more accessible approach so people can use those models. Because we are trained as an environmental scientists and atmospheric scientists, we know how to use Fortran and how to use a batch command and how to run those kind of model. But for stakeholders such as urban planners, decision makers, they won't be able to do that. So there are a few challenges here. I'll list some challenges here. The first one is the installation, right? In order to run these models, we first need to install those models. And for people who are not familiar with the operating system, they will ask lots of questions regarding, you can find like the CSM forum, you will find that people ask lots of questions. And also here, I just list some prerequisites for the software that people need to install. And then the compatibility, if we regarding the version, right? So if we install a software for a certain version, then it might doesn't work for the other software with a different version. So that's one of the challenges. Second one is the configuration. Even though we have the model ready, we need to figure out how to do the configuration, how to set up that so people can run the models in different for different machine. So that's also a big effort. It's very difficult to handle that. Last but not least one, we also have the issue with the data, right? In order to run the model, we need to have the data. Like CSM, it has the routine, the framework, the workflow to download data. But again, like if we want to have our customized simulation, then we need to know how to modify the data, how to make use of the data. So those are the challenges regarding how to make use of the model. So what we did is like we try to make use of the Docker container. You can consider this as a virtual machine. It's an operating system independent containerized application. We call this as an app. It's more like you use your iPhone or Android and then you download the app and then it's ready for you to use. So there's a similar way. Yeah, I know like CSM tutorial also have a similar thing for this. Here we also developed a Python-based tool. This is very specific to the urban climate modeling or urban land surface modeling. We have all the commands ready for people to make use of this. So that means once we download the Docker or the other container-based software, then we can pull this image and then we can run this. You don't need to install any software in addition to this one. So we have the Python package here. So if you are interested, you can try this Python package, and we have the publication in the environmental modeling and software to provide more details regarding how to use this and how we develop this. Then so far I have introduced the global scale modeling here and the local scale or single point simulation here. I won't dive into the micro scale because that's a part of the CFD. So I'm not a CFD expert, so I won't dive into this. However, you can find that there's a gap between the local scale modeling and the global scale modeling. So that's more like the regional scale modeling, right? For the regional scale modeling, people already develop lots of, I think Chen is also familiar with this. We have the WRF, the single layer one, the BEP, BEM one, the ASU model, and the Swiss model is from the UK. And then we also have the CSM kind of version of the ELM urban. Then we are thinking about, can we develop also combine the CLMU to join this big family and to see if this model is good or not. And it's more like a multi-model comparison, but in order to do so, we first need to have a CMU version. Then that means the CMU is not only for the assisted model, but also can be used for the weather, the operational weather kind of services. So CTSM, because CMU is a part of the CTSM. CTSM has already been incorporated into the WRF, but there is no, like the workflow regarding how to run the CMU is not ready. So we developed the whole workflow to run the CMU. For example, we need to know how to generate the static surface data. Then we need to perform WRF-only nested simulation, and then we conduct a WRF CTSM simulation for the domain that we are interested in. And then we do the comparison. The color represent, the gray color means the better model performance, and then we compare the default, the WRF one, and with the CMU one, and then we use data from multiple sources, like from the airport, from the Manchester airport. Then we'll have some stations in the urban areas, and then we do the comparison. So the conclusion is like, for some aspects, the WRF, with the default urban land surface model is good, but for some aspects or some areas, some locations, we find that if we use a CMU, then we can get a better performance. So actually, that's a point why we want to develop a new model, to have this kind of new combination in order to simulate the urban climate. We want to see the variance, and then we want to use this for further development. So this paper, the preprint of this paper is available, and Chen Lin is one of the co-authors. Now we fill out the gap, right? We have the local scale modeling, we have global scale modeling, now we have the meso scale modeling for the regional simulation. And hopefully we can use this to study the regional weather and climate, such as the UK, and to test the effectiveness of this approach. All right, so that's for the multi-scale modeling part. Now I'm gonna dive into the enhanced urban land surface modeling. I'll give some examples regarding how we try to enhance the capability of the CLMU, the urban land surface modeling. All right, so for the CLMU, it has 3 classes. What I mean 3 classes is like for each single grid cell, we have the urban areas, but for the urban areas, we have different types of the urban areas. When CLMU was developed, it has 3 or 4 classes. We have the tall building district, we have the high density and the medium density. Then you may aware like they might not fully represent the diversity of the heterogeneity of the urban areas, and this data was developed like 15 years ago. So it's how CLMU was how when we run CLMU, we will have this different we have those land type for the urban areas. However, for the urban planners, they are interested in a model called a scheme called the local climate zones. I don't know how many of you have heard local climate zones before. Okay, yeah, we have already know what is local climate zone. So it's a classification system used to describe the urban heterogeneity. So like we have LCZ1, that's a compact high rise, right? Then we have LCZ2, that's heavy industry, and then we have LCZ5, like open mid-rise. So it specifies different land type. Now we have 10 types of the urban. So it's not just simply increase from 3 to 10, because LCZ is widely used in the urban planning and the stakeholder. So this is very important for them to do the decision making. So this motivated us to develop the LCZ-based scheme for the CLMU. So what we did is like we add a new scheme to the CLMU source code, and then the users will have the option to either use LCZ or not use LCZ. And if they choose to use LCZ, then we have the 10 types of the urban areas, and then we will have the new data used for this one. And the paper also has been published last year. We recently, we got a grant last year to work on this this field. So our plan is to have a global scale LCZ data, the LCZ based urban surface parameter, so that we can use that for the urban climate projection and adaptation in the future. So if you are interested, we can talk regarding how to collaborate on this one. So that's one of the reasons why I visited NCAR today. The second use case is about urban climate adaptation. It's about albedo. So albedo describes the reflection ability of solar radiation on a surface, right? So, for example, we have the asphalt. It's dark, and the albedo is very low, 0.05. And for the snow, it has a very high albedo, right? Then we have the sunlight, then they will have the different reflections regarding the sunlight. So people are using this property to study how to do the urban climate adaptation by changing the surface, the albedo of for example, the rooftop. For example, if we use low albedo, we can maybe just we will absorb most of the sunlight, and then it will be warmer. Then if we are high albedo, then it can reflect most of the sunlight, and then the surface will be cooler. So that's a motivation why we use albedo to modify the albedo to do the urban climate adaptation. So when people do this kind of experiments, they will set up two cases, right? The first one is like they will use a low albedo, set albedo value like 0.05, and then over 50 years to run the simulation. Then they will have another case to run albedo with a high albedo for the same time period, like 50 years. Then you will find a problem, because when using those albedo, they keep as a constant, doesn't change or it doesn't evolve along with time. So this will introduce a problem like, then what if the curve is like this, right? So current CSM model doesn't provide the capability to do that. For sure, there is a feasible but not a recommended approach. Like we can run the simulation like for 10 years, then we stop the simulation, then we change the urban surface data, then resubmit the job and run that again. Then we stop again, then we modify the urban surface data again and then run that. So this is feasible, but not recommended. What if when we change this and then put it into a queue and then wait for several days, right? It's out of our control. So this way is feasible, yet the setup process is very complicated, and also we cannot account for the time regarding the modification, the queuing. It will take much longer compared than what I'm showing here. So what we are thinking about is like, can we add a time dimension to the albedo so that we can run the simulation smoothly? That means we set up the albedo over time, and then it can run the simulation at once, and we don't need to stop and restart, stop and restart. By means of this, we can use this to simulate different adaptation strategies like here. We can start with low albedo, but we can follow different trends, right? We can increase albedo rapidly and then slow down, or we can gradually increase albedo, or we keep it as a constant, and then we can evaluate the effectiveness, because we can map this to the real-world decision making. Should we put more efforts in the very beginning, or should we put more efforts in the end, or we should keep the consistency in order to do the adaptation strategies? And this paper was published 2024. If you are interested, you can. We call this as you can take a look at. We call this as a transient urban surface albedo representation. And also, it's not only for adaptation. We can use this to study the wear and tear, the natural processes of the albedo, and then have a better, more realistic representation of the roof, the albedo. It's not only for roof, but also we can use this for wall, for road, and then to evaluate the effectiveness of different adaptation strategies. We know, as I also mentioned, like we have the building energy model within the CLMU. So that means the building energy is a very important part compared to the within the anthropogenic heat. On the other hand, recent studies also found that traffic heat also accounts for a certain proportion of the anthropogenic heat. So our recent work also start to focusing on the urban traffic heat flux. The idea is like we will introduce we will connect the traffic model or the output from the traffic model and the associated anthropogenic heat. We introduce that into the CLMU. So basically, we have the traffic model here. Then we can have the traffic heat flux, and then it can be coupled into the urban canyon model. Then it will we will have the iteration through the pervious road, impervious road, and then we can have a cycle like this. Also, we can take the weather into our account. For example, if we have the snow and the rain, then we might slow down our speed, and then the anthropogenic heat will be different. So this is something we are currently working on. And if you are interested, you can take a look at our urban traffic heat. This preprint. Basically, you can find the details regarding implementation and our assumption regarding how the urban traffic heat will influence the urban land surface model. All right, so now I'm gonna get into the topic regarding the AI and the cloud computing for urban land surface modeling. In the very beginning, I want to introduce a new approach called automated machine learning. How many of you have heard this before? Okay, so that's good. So I can provide more details regarding automated machine learning. So I know like most of you already know or at least heard of the machine learning. This is a new paradigm because automated machine learning is developed to help us what I mean us is a domain scientist to implement a machine learning approach. We use the air quality in India as a test bed to demonstrate the usage of automated machine learning. And we published a paper in 2023, which has been highlighted by the AGO editor. And the title is Unleashing the Power of Automated Machine Learning for Atmospheric Research. Why do we use automated machine learning? Let me give you an example, okay? So in order to do the machine learning studies, first we need to select a model, right? Some people, they might be interested in random forest. Some people, they might be interested in XGBoost or Light GBM. Or some people might prefer deep learning or some people say, also I mentioned linear regression is a kind of a machine learning model. So people already have different choices or preference regarding what kind of model they want to use. So in machine learning, it's called a learner. We need to decide a learner in order to train the model. Then on the other hand, once we decide a learner, it involves lots of decision making. So give you an analogy, when we want to run WOLF, we have different parameterization scheme, right? Then for this area, the microphysics scheme might be better, and for different area, it might be different. It's similar for machine learning. Once we have a machine learning learner, a fixed machine learning learner, we need to tune something called a hyperparameter, like the Light GBM. You can have 5 decision trees, or you can have 1,000 decision trees. So it really depends on the user decision. It's not by the model itself. It's once the user decide 5 decision tree, then the model will train based on 5 decision tree. Once the user say 1,000 tree might be better, then we will train a model based on the 1,000 trees. So it evolves in decision making. So you can see there are lots of decisions to make if we want to use machine learning. And also those are not different stage. Basically, if we want to use a random forest, then we need to test the different parameters for all the random forests set up. If we want to use Light GBM, we also need to test a different hyperparameter combination for Light GBM. So those are in parallel. We need to have lots of experiments in parallel. So this is kind of optimization problem, right? We need to optimize the best learner, I call it the best learner, or the best hyperparameters for that learner. And also, we cannot select the learner first and then to the hyperparameter. We need to do this in parallel together. This actually is a problem like that mathematician or statistician or computer scientists that are interested. So they proposed optimization solutions, and then they incorporate that into a software called automated machine learning. The package that I use is actually developed by Microsoft. They developed a automated machine learning package, and then use this for different tasks. And we borrow this in environmental research and demonstrate the effectiveness of automated machine learning. So we use this in addition to the air quality studies that I just introduced at the very beginning. We also implement that to the urban climate emulation. Like what I say emulation is like we have the feature from atmospheric model, and then we want to estimate the 2-meter temperature from the land surface model. So we use automated machine learning to train a wide variety kind of model, because for different location, for different combination, they may end up with different machine learning model and hyperparameters. For example, if we we use 3 model as a test bed. We have linear regression, we have XGBoost, then we have the automated machine learning by Microsoft. And then we try different combination of input variables. We try the CAM, the atmospheric model as a feature, and then we incorporate the location as a feature. Then we also try the combination of atmospheric model and urban surface data. And then we also try the combination of all of them. So it's like you are doing the experiments, and we try to have the control group and have the experimental group, and then to evaluate the effectiveness of different new variables. And then we also try the current and the future. For example, we train a model based on the historical data, and then apply that to the future projection. Then we also try to train a model based on future, because we based on the simulation from CSM. We regard as a ground truth in order to evaluate the model performance. Then we try to see, to evaluate the temporal extrapolation to see how good the model is. For example, if we can train a current model, then it works very well for the future model. Then in the future, it boosts our confidence regarding how good the current model is, right? Then we don't need to worry about the temporal extrapolation in the future. Then we do lots of experiments. We also try the spatial extrapolation to see, like, for example, we train a grid in Boulder, and then is it good for like Utah or the other locations? We do lots of experiments. And the motivation why we use automated machine learning is that, for example, if the combination like this, maybe random forest will be the best model. Then if we try the combination like this, maybe XGBoost can be the best model. And also the hyperparameter will be totally different. So that's a motivation why we use automated machine learning. We don't want to use a single model and feed that for all the locations or for different time periods. We want to have the dedicated model for the dedicated use case. So that's for the automated machine learning. And the reason why we build automated machine learning is that we are not claiming the automated machine learning is the best solution, but the automated machine learning can be the better baseline compared to the user-defined solution. For example, people will always use linear regression to demonstrate the linear model is not a good choice. Or some people, they will use a random forest or XGBoost when demonstrate the neural network or the approaches that they develop to be the better solution. Here, we want to argue that automated machine learning can serve as a better baseline. So if we want to develop a new model, we need to beat automated machine learning. So that means we have a higher threshold in order to develop the model, a higher bar in order to develop a model. Recently, we also start working on physics-guided AI model, and this work has been published in Europe. The DOI is still not available, but it's a top AI conference. I showed the metric, although I should not show the metric. It's a top AI model. If you take a look at Google Scholar, and there are different AI. It's a top AI conference. And then if you take a look at Google Scholar, you will find some top AI conference. And in the field of computer science and AI, they are more focused on the conference over the journals. And what we are doing here is like we try to develop the AI-based model and see how good it is, like based on the view of computer science or AI community. So what we are doing is like we use something called a cross-attention. Cross-attention is like we develop this model is based on the transformer. So for those of you who are not familiar with transformer, when we talk about the GPT, T means a transformer. So transformer is the core of this model. And what we are doing is that we use something called a cross attention. So we have the atmospheric forcing data here, and then we have the urban land surface data here, and then we will do something like called embedding. So that means we intentionally group them, combine them as a group, and then we use something like cross attention, and then we use self attention, and then we do some cross attention again. The idea is like based on this model, we not only estimate the 2-meter temperature for urban areas, but also the other variables such as humidity and the geo temperature as a test bed. So what we found is like if we train a model based on this, and then we consider this a kind of foundation model, and then based on this foundation model, and then we use some real-world data to fine-tune this foundation model, we find that this model even outperform the numerical model that we developed. So that means we train a model based on CLMU, then we update the model a little bit based on some pieces of the real-world observation, and then we compare this model with CLMU. We find this model has a better performance. So that demonstrates the usage of AI. For sure, now we just use 3 variables to give the example. In the future, we want to have to incorporate more variables, and this will be more complex. So it can complement what the current people are working on regarding the weather model, because the land surface model can be the land surface model that we develop here based on the AI approach can be incorporated into the weather model to provide a better urban weather and the climate. Then here I also want to demonstrate a case study that using cloud computing. We already introduced what is the CLMU app that's based on the Docker container, the virtual machine I just mentioned, which is resolve the issue regarding the installation and the model simulation. And then we found it's still very difficult for stakeholder to use this model because they don't want to use Python, or they don't want to use a bash command in order to do that. And they prefer an interface that they can interact with, and then they will be easy to use. So what we did is like we sold this this idea to AWS, and they are very happy to sponsor us and provide some credits for us to develop the cloud-based model. And we use some data, like the 1 kilometer data developed by Professor Lei Zhao's group, and then we use this for the global scale. So ideally, you can do the simulation for any location over the world, as long as those are the urban areas. And then currently, we also incorporate the local climate zones into this platform. And then let me show you a demo here. So if I click, so we have the interface like this, and then you log in, and then you can find a map. Different color means different local climate zones. And then you zoom in here, Manchester, and then you can see different local climate zones. Then we will pick up a location, then you can see latitude, longitude, and then we will extract the urban surface data for that location. Basically, you will see the urban surface data like the albedo and other variables that you are interested in. And then we will set up the start date for the simulation, like we set up the November 1st, and then we say like we will run a simulation for 3 days. And then you can get the simulation, the output, and then we can study the different metric like the urban heat island or other metrics for our analysis. And then we can download the data. We can download the urban surface data, and also we can download our simulation data. And then you can also upload your own data. All right. So that's basically what I want to introduce today. I first introduced the multi-scale urban land surface modeling. And then I also introduced the enhanced urban land surface modeling. I used some examples such as local climate zones, the albedo, the traffic, the heat flux from the traffic. And then I introduced the AI and the cloud computing based on modeling. I introduced automated machine learning as well as the physics guided AI model. And for the more accessible platform, I used cloud computing as an example. Like we use the cloud computing empower the platform to make the model easy to use and to reach to wider audience. All right, so that's basically my talk. Thank you for being here. I'm happy to take any questions.
Okay, questions from audience.
So for two questions. First one, in your visualization tools, do you think about include a chat box?
You mean the visualization for that platform, right?
Yeah. Like you can just speak to the agent
yes.
just tie the chat to the
Yeah, so that's indeed
you have to
yeah, so that's indeed the project that we start working on that, because I also saw some posts from a professor at University of Illinois, like Steve Nesbitt. He also showed how we can interact with ChatGPT and to get the data, and also some supercomputing center in the Europe. When you use a chatbot say, I want to get a CMIP data, and they will retrieve the data for you. So we are interested in this kind of field, and we want to incorporate that into the cloud computing. But one thing we need to think about is the cost, because for example, if we want to use the open source like model like DeepSeek or Llama by Meta, then it's free, but we need to think about how to implement that into the platform, because that's not a small model, that's a big model. Yeah.
And then second is, can you talk more about if you train the historical data, are you able to project the future climate? Like, I tried that, but I think the machine or the deep learning cannot extrapolate temporarily to the future.
Yeah, that's also a very good question. You are talking about the temporal shifting of the machine learning model. So in our study, because we train a model based on historical data, and then we apply that to future data. Those are all based on CSM. So within the context of CSM, it's okay. We didn't find a large difference between, compare the model performance by training the historical data and training based on the future data. It's okay. But on the other hand, I'm working with people in computer science. We try to incorporate the temporal shift into the machine learning model. So the machine learning model, to some degree, they will account for the temporal shift. So if you are interested, I can share that paper to you, and then you can take a look at how the model can capture the temporal shift in your data and then provide a better performance. Thank you.
Ethan.
Thanks. It was a really interesting talk. I'm sorry I missed the first 5-10 minutes. If I'm correct, you did a comparison between the WRF urban canopy model and the CLM urban canopy model. But to do that, you had to be running NOAA MP in one and CTSM in the other. So I'm wondering how much you think that what you see in your results might be driven by the fact that you have different land models underneath it versus how much is coming from the urban model.
Yeah, so that's a very good point, because honestly, we have to compare them as a whole. So what we're doing is like the WRF CMU and the WRF like the NOAA to do the comparison. We cannot separate out the interactions between the forcing data and the urban data. But so it also is a long-standing problem in all the fields. It's very difficult to separate the contribution of different components, right? So what we do is like we just say, yeah, that's from WRF CMU, that's from WRF NOAA, and we want to evaluate the performance of, yeah.
One thing I think Zhonghua student did is that we use the urban specific measurements to compare with that urban output only, not the grid level mean, if I remember correctly, because the urban portion of the temperature.
But I think there might be some influence from surrounding grid
Yes,
cells.
there is.
Right?
So
Yeah.
it's a couple rounds.
Yeah.
But also-
Yeah, it's a couple. Yeah.
Okay, then I can provide some
Yeah, yeah.
idea. Actually, the piggybacking methodology can be actually used.
Oh.
If you can swap the physics with the, so you drive your whole round with your WRF CTSM, and then when you call, after you call the CTSM land surface step, you call another land surface the other land surface model, and that dynamic will not be feedback because you only look at the, under the sand kind of a couple dynamics, what the physics response will look like. But you need to run it twice to switch the physics within that run to isolate whatever the dynamic interactions should be. But this has been demonstrated useful for like microphysics effect, but no one tried it for other physics yet.
I think we tried that for the snow ones. Run the snowpack radiation transfer twice within one time step to with and without aerosol. So then you can quantify the aerosol impact without with everything stays.
That's a
same.
one-time step thing? Or,
Yeah. No, every time step.
But then, yeah, as long as you don't have the feedback, yes, and then you can use that that way.
Yeah.
But we can talk.
But it's good.
Yeah, that's very good suggestion. Yeah.
I do have a question for your physics guided machine learning. So can you provide a bit more background information about where does that physics guided go into like the part C?
Yeah. So part C.
Yeah, the physics guided. So where does the physics go in this diagram? In this.
Yeah, so let me go through. Like in the very beginning, we try to incorporate physics knowledge, right? We know those variables are the atmospheric forcing, and those variables are the urban surface data. So we won't let them all of them to interact with each other, right? And then we here we try to use a cross attention, and then we use the to have the QKV to query kind of thing, and to make them to interact with each other. And then here is like because we have the encoder kind of here is the encoder, and then we have the decoder. Then we know there's the connection. They have the relationship between those variables, right? Then we so intentionally have them to interact with each other, and then we try to have the linear combination, and then to have So you can read our paper for more information regarding how we intentionally design this architecture. Yeah, because it's I think the key point is like first you need to consider the embedding. Yeah, we don't want all the variables interacting with each other because it will bring noise and the information that we are not needed for the modeling. Yeah, but here also we have the QKV, which is attention. So if you are interested, you can take a look at here.
So I assume the embedding step is more based on your domain knowledge and experience.
Yes, yeah.
So just following on that, does that mean you're also forcing some of the latent states to match physical variables in some ways, so that you're imposing somewhere deeper within the network a physical meaning to things?
For our architecture, we might not consider this. I need to double check. But we do have our model available. If you are interested, you can take a look. Yeah, we have the Hugging Face. The model is available there, and we have the document. And then once you deploy the model, you can run the model by yourself. Yeah, within your GPU. Yeah.
Any other questions? Any questions online? Okay, no. Okay, if there's no other question, let's thank Zhonghua again.
Thank you.
If you want to have an individual talk with Zhonghua about AI, ML thing, feel free to look for him or let me know and I can arrange a meeting.
Where is his office?
He does not have an office.
Oh.
He's here only for 2 days.
Yeah.
But right now, temporarily, so he just sits outside my office.
The
So-
cubicle area.
Yeah.
Okay.
Yeah, so you can find him there.
Yeah.